gets a little smaller with the larger the sample size gets, which makes sense. The larger the sample size, the larger number you're dividing by, and you get to see a lot. So I think that's their goal here. You start with 50 and then you went the same thing to 250. So what happened? It made your standard deviation a little smaller. So rule, as your sample size increases, your standard deviation will decrease, will get smaller. As the size of a sample increases, the mean of the distribution of the sample mean increases, the mean stays the same. The mean of your population is equal to the mean of your sample. That's going to stay the same. A sampling distribution is normal only when the population is normal. That's one condition. The second condition is n is greater than or equal to 30. Automatically, no matter what the population looks like, if your sample size is greater than or equal to 30, then you have a normal distribution. You okay with that? That's going to come back to haunt you. You've got to remember those two things. Okay. Number 9. Okay. The waiting time in seconds at a traffic light. They wanted to know which one does this represent. Now, here's your mean. Here's your standard deviation. And if you kind of noticed where the means fall, the means kind of all fall in the middle here. So the means are kind of looking about the same. Now, the reason why they changed this mean is because they wanted to see if you change the mean of your sample. Yes?
How about 1.19?
I have the wrong one?
If you have a maximum, what you got is an extra one.
Divided by 10, 1.19. Yeah, 1.19. Absolutely right. 1.19. I left out a 1. Because you're just moving this one decimal over. Thank you. Who caught me? Marissa, thank you. But the reason why they changed your mean is because they wanted to see, does the square root of the 10, square root of 100, which is 10, is it going to change the decimal in your mean? Your mean is not going to change. So therefore, get rid of anything that changed the mean. Now you're looking at your standard deviation. Now if your standard deviation stayed the same, then you had a population, not a sample. So even without the calculations, you could kind of get to this guy. The standard deviation had to change, right? Your sample size changed. Your sample size went to 100. So that had to change our standard deviation. So we can kind of rule out B, because the mean can't change. We can kind of rule out A, because your standard deviation didn't change. So you're kind of left with C, even without doing all this. But this kind of makes it a little bit better. Okay. 19. Now, I don't know what happened here. Something happened. I think it happened when we were playing with that word thing, so we'll have to, like, work around this. I don't know where these little things came from. Yeah, it kind of shifted all my stuff up. So I think it happened when I was doing this with his word before he changed my word on me and got everything back to normal. I think it condensed.
25 and 19.
Put together, yeah, I have no space for, if I could move this down, this might work. It might show me the space for 19. Let me try that and see if this, it's been doing weird things since he fixed my word. Looking better?
Yeah.
He fixed this, but now a lot of the ones that I did when it was on there have to move.
Oh, yeah.
And here's another one. Just a little weird. It's okay? Okay, so let's see this before I do anything else. Alright. Let's look at 19. 19 says that braking distances from 60 miles an hour to a complete stop, that they're normally distributed, and it has to tell us that. Good? Normally distributed, and it has a mean and a standard deviation. Random samples of 12 are drawn. So when your n is less than or equal to 30, we have to tell you that the population was normally distributed. If we did not say that, you could not apply the central limit theorem here. The central limit theorem says change your standard deviation. So we could not do that if they didn't tell us that. So we took out our random samples. Remember, your random samples is the n. Okay, now we have to find the mean and the standard error of the mean. The standard error of the mean is what they call the sample standard deviation. They refer to that as sample, the standard error of the mean. And your mean is going to stay the same. That stays. Your standard deviation is going to change. So you're going to take the original standard deviation over the square root of how many you have in your sample. Generally, if the standard deviation in the original problem, use those decimals. If they don't have any decimals, you can go to 2 or you can round it to whatever they round to. We're going to kind of see a little bit more with this when we play with the probability part, because then we start to make the sketch a little bit more. Now, in this one, 25, I wanted you to do 25 because it gave a nice comparison. This we used 12, then we used 24, then we used 36. So we should see that this standard deviation would therefore be the largest, and the one with the most should be the least, because we're dividing by a larger number each time. So, and we can see that. So we can see as we get a higher sample, we get a little bit more exact in our measurements. So the means are going to stay the same, but again, we see as the sample size gets larger, the standard deviation gets smaller. You okay with these? Kind of basic. Any questions on this? Is what we're going to use. Your normal z-score says x minus the mean over the standard deviation. We're going to change this slightly. So now, instead of x, we use the mean of the sample means, x bar. This is the mean of the sample means. Remember, I told you this is kind of like a little tongue twister. If we took all the samples, took their average, then took the average of all the averages, that's the x bar. And the only other change is we have to adjust the standard deviation. This change you won't even see at all, because we're going to call it the mean of the sample means in the problem. But this is the one change you have to make. Now, sometimes kids like to go make their standard deviation first and then put it in here, because it's a little easier in the calculator. But just be careful of your rounding. You don't want to cut this off too sharp, without enough rounding, because you should really save your rounding for the end. If you put this in your calculator, this has to get parentheses, this has to get parentheses. If you use a fraction bar, you would be okay. And on the yellow calculators, you can use the fraction bar. And then you don't need the parentheses. In the 83s, the black calculators, you have to use parentheses. So just something just to be aware of, because the calculator throws everybody off. You guys are pretty fortunate with the fraction key. Years ago, we didn't have that. Until we got the new software, we didn't have the fraction key. What's going on here? All right. So let's take a look at why we use this. All right. Example 4. You randomly select 50 drivers age 15 to 19. You ask the question, what is the probability? I got a probability statement. When I ask for a probability, what kind of number do I get? A percent, a decimal that I can convert to a percent or leave it in a decimal. I want to know the probability that the mean time spent driving each day is between these two numbers. So my x bar is between these two numbers. there's my probability statement. They give us the standard deviation. The mean, you have to go to the chart that's right on that page. Find the drivers age 15 to 19 and tell me what their population mean is. In your book. 25? Thank you. They have to give you this piece of information or you have no place to start. So they gave us the population standard deviation. A lot of times they don't get the population standard deviation until later because they have to run this a few times. Okay, so now we're looking at something that was spread out like this, and because we're going to change your standard deviation, is going to go like this. What we do is only graph the small one. If you graph the large one with that standard deviation, then you put on top of it the small one, it's really impossible to see where your z-scores are because you changed your whole x-axis. So all we're going to do is graph the changed one, the one for the sample. So we're going to find your sample standard deviation just so that we can make some kind of sketch. So 1.5 over the square root of what's n? 50. Okay, so we're going to find your sample standard deviation. So, let's get this done. I don't have to add or subtract. And I like the sketches. I know I'm a pain, but I like the sketches, and I think a lot of you are seeing why, because you know where's positive, where's negative. So when you find your standard deviation, oops, just try it. Your new standard deviation is 0.212. Okay. Now when you make your curve, your sketch, should you want to make this, the mean stays in the middle, and you're going to add and subtract by 0.212. If you did this guy, the large one, at 1.5, and then you tried to put the small one on top of it, it's really impossible because your bottom line, your x-axis, is your z-scores. So I would have to take this original one and then redo my lines 1, 2, 3. So you don't want to put 2 on top of 1. All you want to do is the small one. That's the one we're looking at. So if you add each time 0.212 and whatever you want to call this, what did we get there? So you're not really moving by much. 25.212, you can make it 2 decimals, whatever you want to make it. 0.424 and keep on going. So we need to be between 24.7 and 25.5. Go high enough so that you get to see where you're going to. 6 something rather. So somewhere right in here. And somewhere right, take this one down. 24.7 something. So it's somewhere over here. So we're doing this area in here. And if you were going to give me a guesstimate about your area, what would you say? A guesstimate. How big does your area look?
More than 60.
More than 60. How much is this area from 0 to the negative 1? Half of 68. What's half of 68? 32. It's 34. Somewhere right in there. And this is pretty far. So 68, 34, 32, whatever you want to estimate. It's only an estimate. Even if I said 30, if 30's in here, this is slightly less than 50. So if I said 40, 30 and 40, that puts me in the 70 bracket. Just give it a guesstimate. So if my answer comes out to be 10, I know I'm crazy. So what you're going to do now, and we can do this on your calculator, I'll do it on your calculator as well, is you're going to find your z-score for both of these. You're going to find your z-score, you're going to find your areas, and then you're going to subtract your areas. I'll do it on your calculator as well. You can use your calculator for this just as easy. When you put your standard deviation in, put it in and let your calculator figure it out. So this z-score comes out to be negative 1.41. And this z-score comes out to be 2.36. Look up your areas and subtract your areas. And we were higher, but we're still around the ballpark. We're still a good chunk of that curve. Don't subtract those areas from 1 because you're going to subtract and find a difference between them. Now, if you do this on your calculator, you can still do this on your calculator. Second VAERS. Okay. When we did your normal CDF, and we put this information in, you can put your standard deviation right here. So if my lower limit is 24.7, for those of you that like to use the calculator, and my upper limit, especially in between, works really nicely on this. The mean is 25, and put your standard deviation here. 1.5 divided by the square root of 50. Let your calculator, oops, that didn't work out well. And that's square root. Let's take a mess. There it goes. Okay, and now paste. Let your calculator do this part. Oops, I got 0. All right, so let's see what I did wrong here. Other than the fact that my calculator never wants to work over here. Only works on this side. Oops, my mean. And did we come out with the same answer, ballpark? This is more exact because your calculator, we rounded to z-scores. We looked up the areas ourselves. So you're not going to get the same exact answer when you use your calculator, but let your calculator do the tough part for you. We've done these before. We've done the in-betweens. All we're doing is changing your standard deviation. So out of a sample of 50 drivers in this age bracket, 15 to 19, about 91% of those drivers will have a mean between 24.7 and 25.5. The mean of the sample means. Of all the samples that we took and all the averages that we took, their averages will be between those two numbers. A lot higher than if we did a population, because your curve is a lot more squished together. But again, try not to do both because you'll end up changing your x-axis, you'll end up going crazy. Does this make sense? Same thing, probability statement, graph, set this out. The only thing different is right here. This is the only different thing. Everything else will work the same. Okay. Let's try another one. Okay. This one is going to ask us to find 100 drivers and see what's going to happen to this. So we did a 50, let's do 100. What happens to the standard deviation if we increase our sample size to 100? It gets even smaller. So do you think we should cover more part of our curve or less of our curve? Okay, think again. Your standard deviation is smaller. So are you closer to the mean or further from the mean? Closer to the mean. So should we cover more of our curve or less of our curve? More, right? So let's try this. We won't do a graph this time. We'll just set this up. We still want the probability statement to be exactly the same. These are the mean of your sample means. I think they kept everything else the same. Now our standard deviation is divided by the square root of 100, which is divided by 10. If you divide by 10, your sample standard deviation becomes 0.15. Before, it was 2.12. See, it got smaller? And your standard deviation got smaller. Okay, so now, your z-score comes out to be negative 2.0 and 25.5. This z-score comes out to be 3.33. Don't forget, you're close. Everything's closer to the mean. When you subtract your areas, you get 9768. Almost 98%. Almost 98% of the sample of 100 drivers will fall between, the mean of the sample means will fall between 24.7 and 25.5. You just make a much tighter curve. That's all that happens to this. The probability statement stays the same. Your sketch is going to go based on your sample, not your population. And it's going to show us this. Now, before I go to number 5, I'm going to run out of time. Okay, tomorrow when we come back, I don't want to start with number 5. I want to go down and compare a population to a sample. I think that'd be easier for you to see the difference.